Let me tell you about something that has haunted physicists for over a century, a mystery so profound that it challenges our deepest assumptions about reality. The universe, despite all appearances, cannot be random. The evidence is overwhelming, and the implications are staggering. Everything is designed. I don't mean designed by a supernatural being, though I'll address that possibility. I mean that the universe exhibits a level of precise organization, of exact calibration, of intricate fine-tuning that simply cannot be explained by chance. The numbers that govern reality, the fundamental constants of physics, are set to values so precisely specified that even tiny deviations would make existence impossible. This isn't philosophy or speculation. This is physics. This is mathematics. This is the hard evidence of decades of measurement and calculation, pointing toward a conclusion that many scientists find deeply uncomfortable. Randomness cannot explain the universe we inhabit. Let me take you through the evidence. Because understanding why the universe cannot be random requires confronting some of the most remarkable facts we've discovered about the nature of reality. Let me start with the fundamental constants. The universe is governed by numbers. Not just any numbers, specific numbers with specific values that determine everything about how reality works. These are the fundamental constants of physics, and their values are among the most precisely measured quantities in science. The speed of light, 299,792,458 meters per second. Exactly. The gravitational constant, 6.7430 times 10, negative 11 cubic meters per kilogram per second squared. Planck's constant, 6.62607 times 10, negative 34 joule seconds. The fine structure constant, approximately 1/13736. The mass of the electron, 9.1093, 8 times 10, negative 31 kilograms. The mass of the proton, 1.67262 times 10, negative 27 kilograms. These numbers, and about 24 others, completely determine the physics of the universe. Change any of them, and everything changes. The question is, why do they have the values they have? In a random universe, these values would be arbitrary, set by chance, with no particular significance. Any values would be equally likely. The constants might just as easily have different values, and the universe would simply be different. But here's the extraordinary thing. The values are not arbitrary. They are tuned with exquisite precision to values that allow complexity to exist. Change them even slightly, and the universe becomes sterile, lifeless, incapable of producing stars, planets, chemistry, or life. This is the fine-tuning problem. The constants of physics appear to be designed, calibrated precisely to permit existence as we know it. Let me give you specific examples. The first example is the strength of gravity. Gravity is the weakest of the four fundamental forces, about 1036 times weaker than electromagnetism. This seems like an arbitrary number, but it's not. If gravity were slightly stronger, say, by a factor of just a few stars would burn through their fuel much faster. A star like our Sun, which has been burning steadily for 4.6 billion years, would exhaust itself in just a few million years. There wouldn't be enough time for planets to form, for life to evolve, for complexity to emerge. If gravity were slightly weaker, stars might not form at all. The gravitational attraction needed to pull gas clouds together and ignite nuclear fusion would be insufficient. The universe would be a diffuse fog of hydrogen with no stars, no heavy elements, no planets. The strength of gravity is tuned to a narrow range, perhaps 1 part in 1036, that allows stars to exist with the right properties to support life. This is not random. This is precise. The second example is the strong nuclear force. The strong force holds atomic nuclei together. It's what prevents protons from flying apart due to their electromagnetic repulsion. Its strength is characterized by a number called the strong coupling constant. If the strong force were about 2% stronger, hydrogen would be unstable. Protons would fuse together in the early universe, leaving no hydrogen for stars to burn, no water to form, no organic chemistry to develop. If the strong force were about 5% weaker, deuterium, an isotope of hydrogen essential for stellar nucleosynthesis, would be unstable. Stars couldn't produce the heavy elements needed for planets and life. The strong force is tuned to a precision of a few percent. A random value would almost certainly fall outside this range, but the actual value falls precisely within it. The third example is the electromagnetic force. The strength of electromagnetism is characterized by the fine structure constant, approximately 1/137. This number determines the size of atoms, the strength of chemical bonds, the properties of light and matter. If the fine structure constant were significantly larger, atoms would be smaller and chemical bonds would be stronger. The chemistry of life might be impossible. The delicate molecular machinery that operates in living cells depends on bonds that are strong enough to be stable but weak enough to be manipulated. If the fine structure constant were significantly smaller, atoms would be larger, chemical bonds would be weaker, and complex molecules might not hold together. The intricate structures of proteins, DNA, and cellular membranes might be impossible. The fine structure constant is tuned to a range that allows the rich chemistry necessary for life. This is not random. The fourth example is the mass ratio of protons and neutrons. Protons and neutrons have nearly identical masses, but the neutron is slightly heavier, about 0.14% heavier. This tiny difference has enormous consequences. If the neutron were slightly heavier than it is, or if the proton were slightly lighter free, neutrons would decay even faster than they do. The early universe's supply of neutrons would have been depleted before nucleosynthesis could produce helium and heavier elements. If the neutron were lighter than the proton, even by a small amount, protons would decay into neutrons, hydrogen would be unstable. Every atom of hydrogen in the universe would eventually convert to neutrons, leaving no atomic matter at all. The mass ratio is tuned to a precision of about 0.1%. In a random universe, this ratio could have any value. The actual value falls precisely in the narrow range that allows atoms to exist. The fifth example is the cosmological constant. This is perhaps the most striking example of fine-tuning in all of physics. The cosmological constant represents the energy density of empty space, the inherent energy of the vacuum itself. Quantum field theory predicts that this energy should be enormous, perhaps 120 times larger than we observe. But the observed value is tiny, so tiny that for most of the universe's history, it was completely negligible. Only recently, in cosmological terms, has dark energy begun to dominate the universe's expansion. If the cosmological constant were larger, anywhere close to the value quantum theory predicts, the universe would have expanded so rapidly that matter could never clump together. No galaxies, no stars, no planets, no life. If the cosmological constant were negative and large, the universe would have collapsed back on itself almost immediately after the Big Bang. The cosmological constant appears to be fine-tuned to about 1 part in 10, 120. This is the most extreme fine-tuning in physics, a precision so extraordinary that it seems impossible to explain by chance. Let me now address what these examples mean collectively. Each example I've given involves a different constant, a different aspect of physics, but they all point to the same conclusion. The universe is not random. The values of the constants are not arbitrary. They are tuned precisely, specifically, exactly to permit the existence of complex structures. The probability of getting all these values right by chance is astronomically small. If you randomly selected values for the fundamental constants, the overwhelming majority of possible universes would be sterile, no stars, no chemistry, no life. The universe we actually inhabit is extraordinary, a needle in an infinite haystack. This is the argument from fine-tuning. It doesn't prove that the universe was designed by an intelligent being. But it does prove that the universe is not random, that something other than blind chance is at work. What could that something be? Let me now explore the possible explanations for fine-tuning. The first explanation is design that the universe was deliberately created by an intelligent being who chose the constants to permit life. This is the traditional religious explanation, and the fine-tuning evidence has given it new scientific respectability. If the constants look designed, perhaps they were designed. Perhaps there is a cosmic designer who set the values with intention and purpose. I want to be clear. This explanation is not ruled out by physics. The fine-tuning is a fact. The explanation is a matter of interpretation. Many thoughtful people find the design explanation compelling, but the design explanation raises its own questions. Who designed the designer? Why did the designer choose these particular values? What was the designer's purpose? These questions don't invalidate the design explanation, but they do show that it doesn't fully resolve the mystery. It pushes the question back one step from why are the constants fine-tuned to why did the designer fine-tune them? The second explanation is the multiverse. Perhaps our universe is not the only universe. Perhaps there are infinitely many universes, each with different values of the fundamental constants. In most of these universes, the constants don't permit life, but in a few, by chance, they do. We necessarily find ourselves in one of the life-permitting universes because we couldn't exist in any other. This is the anthropic explanation. It doesn't require a designer just an enormous number of universes, enough that some of them, by chance, have the right constants. The multiverse explanation is taken seriously by many physicists. It emerges naturally from certain versions of string theory and cosmic inflation. It explains the fine-tuning without invoking design. But the multiverse explanation has its critics. We have no direct evidence for other universes. The multiverse might be untestable, and untestable claims are scientifically suspect. The multiverse might just be trading one mystery, fine-tuning for another, the existence of the multiverse itself. The third explanation is that we're missing something, that there's a deeper theory we haven't discovered that would explain why the constants have the values they do. Perhaps the constants are not arbitrary. Perhaps they follow from some more fundamental principle we haven't yet understood. Perhaps a future theory of everything will derive the constants from pure mathematics, showing that no other values were possible. This is the hope of many theoretical physicists. String theory, loop quantum gravity, and other approaches to fundamental physics all aim to explain the constants to show that they are not free parameters, but determined by deeper structure. So far, this hope has not been realized. No theory has successfully derived the constants from first principles, but the search continues. The fourth explanation is that the constants must have the values they do for reasons of logical or mathematical necessity. Perhaps a universe with different constants would be logically impossible, would contain contradictions or inconsistencies. Perhaps the apparent fine-tuning is an illusion, and the constants couldn't have been otherwise. This explanation is appealing but difficult to substantiate. We can easily imagine universes with different constants. We can write down the equations and study their behavior. They seem logically coherent, just different from our universe. But perhaps our imagination is limited. Perhaps there are subtle reasons why only our values are truly consistent. This remains a possibility. Now, let me address a crucial point. The fine-tuning is not just about life. Sometimes the fine-tuning argument is dismissed as anthropocentric, as saying merely that the universe is tuned for human life, which is circular because we wouldn't exist to notice if it weren't. But the fine-tuning goes much deeper than this. The constants are not just tuned for life, they're tuned for the existence of any complex structures at all. Without the right values, there would be no atoms, no molecules, no chemistry. There would be no stars, no planets, no galaxies. The universe would be a formless chaos, a sea of radiation, or a void of isolated particles, or nothing at all. Life is just the most dramatic example of complexity. But complexity itself, the organization of matter into structured functional forms, requires the constants to be tuned. This is not anthropocentrism. This is a fundamental fact about what kinds of universes are possible. Most possible universes are boring, featureless, structureless, empty. Our universe is extraordinary, rich, complex, structured. And this extraordinariness requires fine-tuning. The question is not why is the universe tuned for us. The question is why is the universe tuned for anything. In part 2, I want to explore these explanations more deeply. What does modern physics say about why the constants have the values they do? What evidence do we have for or against the various explanations? And what are the implications for our understanding of reality? So we've established the extraordinary fine-tuning of the fundamental constants, the precise calibration that allows atoms, stars, chemistry, and complexity to exist. We've introduced the possible explanations: design, the multiverse, a deeper theory, or logical necessity. Now I want to go deeper. What does modern physics actually tell us about these explanations? What evidence can we bring to bear? And what are the profound implications of the conclusion that the universe cannot be random? Let me start by examining the multiverse explanation more carefully. The multiverse is not a single idea, but a family of related concepts. There are several different versions, each arising from different physical theories, each with different implications for the fine-tuning problem. The first version is the inflationary multiverse. Cosmic inflation, the rapid expansion of the very early universe, is now a standard part of cosmological theory. It explains the flatness and uniformity of the observed universe, the pattern of fluctuations in the cosmic microwave background, and several other puzzling features. But inflation has a remarkable property. In most versions, it never completely ends. While inflation stops in some regions, creating pocket universes like ours, it continues forever in other regions, spawning new pocket universes eternally. This eternal inflation creates a multiverse, a vast, perhaps infinite collection of pocket universes, each with potentially different properties. The fundamental constants might vary from pocket to pocket, determined by random processes during each pocket's formation. If the constants vary across the multiverse, the fine-tuning becomes explicable. Most pocket universes have constants that don't permit complexity, but some, by chance, do. We exist in one of the latter necessarily because we couldn't exist in the former. The inflationary multiverse is not speculation, it's a prediction of well-established inflationary theory. The question is whether we can ever test it. The second version is the string theory landscape. String theory is the leading candidate for a unified theory of fundamental physics. It proposes that the basic constituents of nature are not point particles, but tiny vibrating strings. The different modes of vibration correspond to different particles. String theory has an unexpected feature. It predicts not one unique set of physical laws, but an enormous number of possibilities. The landscape of string theory contains perhaps 500 different configurations, different shapes of the extra dimensions, different patterns of fields and forces. Each configuration corresponds to a different possible universe with different values of the fundamental constants. Our universe, with its particular constants, would be just one point in this vast landscape. Combined with eternal inflation, The string landscape produces a picture in which all possible configurations are realized, each in its own pocket universe. The multiverse contains 10, 500 or more different universes, each with different physics. In this picture, the fine-tuning is explained by selection. Most of the 10, 500 configurations don't permit life, but a few do, and we necessarily inhabit one of those few. The third version is the quantum multiverse. Quantum mechanics, in its standard interpretation, involves probabilities. When a measurement is made, different outcomes are possible, each with a certain probability. One outcome occurs, the others don't. But there's an alternative interpretation, the many worlds interpretation. In this view, all possible outcomes occur, but in different branches of reality. Each quantum measurement causes the universe to split, with each branch containing a different outcome. If the many worlds interpretation is correct, there exists an inconceivably vast multiverse of branching quantum realities. Every possible quantum outcome is realized somewhere. This quantum multiverse doesn't directly explain the fine-tuning of fundamental constants. The constants are the same in all branches. But it shows that the concept of multiple realities is not foreign to physics. The multiverse, in some form, might be unavoidable. Now let me examine the evidence for and against the multiverse explanation. The case for the multiverse rests on theoretical arguments, not direct observation. We cannot see other universes. By definition, if they exist, they are causally disconnected from us. We cannot send signals to them or receive signals from them. The multiverse is, in this sense, inherently unobservable. But this doesn't mean it's scientifically empty. Many scientific theories postulate unobservable entities. We cannot see quarks directly, only their effects. We cannot observe the interior of the sun, only infer it from models. Science routinely goes beyond direct observation. The theoretical case for the multiverse is substantial. Eternal inflation arises naturally from inflationary theory. The string landscape arises from the mathematics of string theory. These are not ad hoc inventions, but consequences of our best physical theories. Moreover, the multiverse explains the fine-tuning without invoking design or coincidence. It provides a naturalistic explanation for why the constants have life-permitting values, because all values are realized somewhere, and we necessarily inhabit a region where the values permit our existence. The case against the multiverse also has force. The most serious objection is that the multiverse is untestable. If we cannot observe other universes, how can we ever know whether they exist? A theory that makes no testable predictions is not scientific, it's metaphysics. This objection has some validity, but it may be too strong. The multiverse might make statistical predictions about what we should observe in our universe, predictions that could, in principle, be tested. If the multiverse exists, our universe should be typical among life-permitting universes. We could ask whether our observed constants are typical and whether our universe has properties we would expect in a multiverse scenario. Some researchers have pursued this approach, though without definitive results. The predictions depend on how you count universes and define typical questions that don't have clear answers. Another objection is that the multiverse doesn't actually explain anything. It just replaces one mystery fine-tuning with another, the existence of the multiverse. Why should a multiverse exist rather than a single universe? Why should the multiverse have properties that guarantee some life-permitting regions? This objection points to a real limitation. The multiverse doesn't provide an ultimate explanation. It pushes the questions back one level. But perhaps this is all we can hope for. Science rarely provides ultimate explanations. It provides better explanations, deeper explanations, but not final ones. Now let me examine the design explanation more carefully. The fine-tuning of the universe has often been cited as evidence for the existence of God, a cosmic designer who set the constants to permit life. This argument has a long history. It's a modern version of the argument from design, which infers an intelligent creator from the apparent purposefulness of nature. The fine-tuning gives this ancient argument new precision and power. The argument can be stated simply: the fundamental constants are fine-tuned for life. Fine-tuning is best explained by design. Therefore, there is a designer. The first premise is established by physics. The fine-tuning is a fact, regardless of interpretation. The controversy concerns the second premise. Is design really the best explanation? The case for design rests on several considerations. First, design is a known explanation for fine-tuning. We know that intelligent beings can set parameters to achieve desired outcomes. We do it ourselves constantly when we tune a radio, calibrate an instrument, or program a computer. Design is a familiar, well-understood explanation for precise calibration. Second, the alternatives are problematic. The multiverse is untestable and doesn't provide ultimate explanation. A deeper theory that derives the constants remains undiscovered despite decades of effort. Logical necessity is difficult to establish. Third, design provides meaning. If the universe was designed, our existence has purpose. We are not accidents but intended outcomes. This resonates with deep human intuitions about significance and value. The case against design also has force. First, design raises the question of the designer's origin. If the universe needs a designer because of its fine-tuning, doesn't the designer also need a designer? And that designer, a further designer? This leads to an infinite regress unless the designer is somehow self-explanatory, requiring no external cause. Theists have responses to this objection. They argue that God is a necessary being, a being whose existence requires no external explanation. Or they argue that the regress terminates in God, who is the ultimate foundation of existence. But these responses are philosophical, not scientific. Second, design doesn't specify which designer. Even if we accept that the universe was designed, we don't know anything about the designer. Is it the God of Christianity, of Islam, of some unknown religion, an alien civilization, a cosmic computer programmer? The design argument points toward a designer but doesn't identify one. Third, design is not a scientific explanation in the usual sense. Science explains phenomena in terms of natural laws and processes. Design invokes an agent with intentions and purposes, a fundamentally different kind of explanation. This doesn't make it wrong, but it does make it different from what science typically provides. Now let me examine the possibility that a deeper theory will explain the constants. Perhaps the constants are not arbitrary. Perhaps they follow from some more fundamental principle, a theory of everything, that would show why the constants must have the values they do. This hope has motivated much of theoretical physics for the past century. Einstein spent his final decades searching for a unified field theory. String theorists have sought a unique vacuum that would determine all physical constants. Loop quantum gravity researchers have hoped their theory would predict the constants from first principles. So far, these efforts have not succeeded. String theory, despite its mathematical beauty, has not produced a unique prediction for the constants. Instead, it has produced a landscape 500 possible configurations, each with different constants. Far from explaining the fine-tuning, string theory has made it more puzzling. Other approaches have made less progress. Loop quantum gravity has not advanced to the point of predicting constants. Alternatives like causal set theory and asymptotic safety remain speculative. This doesn't mean a deeper theory is impossible. Perhaps we simply haven't found it yet. The history of physics includes long periods of confusion followed by breakthrough insights. The right theory might be just around the corner, but there's also a philosophical issue. Even if a deeper theory derives the constants from some more fundamental structure, we can ask why that structure, why those fundamental principles. The question of why this and not something else doesn't have an obvious stopping point. Any explanation we give can be questioned further. This suggests that ultimate explanation may be unattainable, that at some level we must accept certain facts as brute, unexplained givens. If so, the question is, at what level should we stop? Should we accept the constants as brute facts, or should we seek deeper explanations? The fine-tuning suggests we should seek deeper explanations. The constants appear too precisely calibrated to be brute facts. Something seems to be going on, some reason why the values are what they are. The search for that reason continues. Now let me discuss what modern physics reveals about the nature of physical law. The laws of physics, as we understand them, have a particular character. They are mathematical, expressible in precise equations. They are universal, applying everywhere and every when. They are necessary. Things happen as they do because the laws require it. But why these laws? Why these equations? Why this mathematical structure rather than some other? This is the question of the origin of physical law. And it's closely connected to the question of the constants, because the constants appear within the laws. One view is that the laws are necessary, that they couldn't have been otherwise. Perhaps logic itself or mathematics itself determines what physical laws are possible. Perhaps our laws are the unique, consistent set, the only laws that avoid contradiction. This view is attractive but hard to establish. We can easily write down alternative laws, different equations, different structures. They seem logically consistent. Why should our particular laws be uniquely necessary? Another view is that the laws are contingent, that they could have been otherwise but happen to be as they are. Perhaps the laws were set by some process random or designed at the beginning of the universe. Perhaps they vary across the multiverse. This view accommodates the fine-tuning. If the laws could have been otherwise, then the fact that they permit complexity requires explanation. Design or selection via the multiverse provides that explanation. A third view is that the laws are emergent, that they arise from some deeper, more fundamental structure. Perhaps space-time itself and the laws that govern it emerge from quantum entanglement or information processing or something we haven't yet conceived. This view is increasingly popular among theoretical physicists. It suggests that the laws we observe are not fundamental, but derived consequences of something deeper. The constants, too, would be derived, emerging from the underlying structure. But even if the laws emerge from something deeper, we can ask why that deeper structure. The question of ultimate origins remains. Now let me consider the implications of the conclusion that the universe cannot be random. If the fine-tuning is real, and the evidence strongly suggests it is, then randomness cannot explain the universe. The constants are not arbitrary. They are specified. Something has determined their values. This conclusion has profound implications. First, it implies that the universe has structure at the deepest level. The fundamental constants are not accidents but reflect some underlying order. Reality is organized, not chaotic. Second, it implies that our existence is not accidental. The constants that permit our existence are precisely those that actually obtain. Whether this is due to design, selection, or deeper necessity, our existence is connected to the deep structure of reality. Third, it implies that science has limits. We can discover that the universe is fine-tuned, but explaining why it's fine-tuned may require going beyond science into philosophy, theology, or realms we haven't yet conceived. These implications are uncomfortable for some scientists. Many would prefer a universe that is self-explanatory, that requires no external cause or deeper reason. The fine-tuning challenges this preference. But discomfort is not a scientific argument. The evidence points where it points, regardless of our preferences. The universe appears designed, whether by a deity, by selection in a multiverse, or by principles we don't yet understand. Everything is designed, not necessarily by a conscious designer, but in the sense that the structure of reality is not random. The constants are calibrated. The laws are specified. The universe is ordered. In part 3, I want to explore the deepest implications of this conclusion. What does it mean for our understanding of existence? What does it tell us about the nature of reality? And what does it suggest about humanity's place in the cosmos? So we've established the extraordinary fine-tuning of the fundamental constants and explored the possible explanations: design, the multiverse, deeper theory, or logical necessity. We've examined the evidence for and against each explanation and concluded that randomness cannot account for the universe we inhabit. Now I want to explore the deepest implications of this conclusion. What does it mean for our understanding of existence itself? What does it tell us about the nature of reality? And what does it suggest about consciousness, meaning, and humanity's place in the cosmos? Because the impossibility of randomness is not just a technical result in physics. It's a statement about the fundamental nature of reality, a statement with profound philosophical, existential, and perhaps spiritual implications. Let me begin by examining what designed actually means in this context. When I say everything is designed, I don't necessarily mean designed by a conscious being. I mean that the universe exhibits the hallmarks of design, precise specification, functional organization, purposeful structure, regardless of whether a designer exists. A designed object has certain characteristics. Its parts are arranged to achieve a particular outcome. It works, it functions, it does something. Random arrangements don't work, designed arrangements do. Consider a watch. Its gears, springs, and hands are arranged precisely to tell time. A random arrangement of metal pieces wouldn't tell time. The watch's function implies design, either by a watchmaker or by some process that selects for time-telling arrangements. The universe is like the watch. Its fundamental constants are arranged precisely to produce complexity, chemistry, stars, planets, life. Random values wouldn't produce these outcomes. The universe's structure implies design, either by a cosmic designer or by some process that selects for complexity-producing arrangements. This is the core insight. The universe is not random because random arrangements don't work. The universe works, it produces functional outcomes, complex structures, organized systems. Working arrangements are rare. Random arrangements are overwhelmingly non-working. Therefore, the universe is not random. This argument doesn't identify the designer or the selection process. It simply establishes that something other than chance is responsible for the universe's structure. The specification is too precise, the outcomes too functional, the organization too effective to be accidents. Now, let me explore what this means for the nature of physical law. Physical laws are often presented as descriptions of regularities, patterns we observe in nature. Gravity attracts masses. Electromagnetism binds atoms. The strong force holds nuclei together. These are facts about how nature behaves. But the fine-tuning suggests something deeper. The laws are not merely descriptions. They are specifications. They don't just happen to have the form they have. They are precisely calibrated to produce particular outcomes. Consider the inverse square law of gravity. gravitational force decreases with the square of distance. This specific mathematical form has profound consequences. It allows stable orbits, permits the formation of galaxies and solar systems, makes possible the delicate balance of gravitational collapse and radiation pressure that powers stars. If gravity followed an inverse cube law or an inverse 1-5 law, none of this would work. Orbits would be unstable. Stars would either collapse immediately or fail to form. The universe would be radically different and almost certainly hostile to complexity. Why is gravity inverse square? The standard answer is that it follows from the geometry of three-dimensional space force lines spread out over the surface of a sphere, which grows as the square of the radius. But this just pushes the question back. Why 3 spatial dimensions? Why not 2 or 4 or 10? Other numbers of dimensions would give different force laws, different physics, different outcomes. The answer is 3 spatial dimensions with an inverse square gravitational law is precisely what's needed for the kind of universe we inhabit. It's not random, it's specified. This pattern repeats throughout physics. Every aspect of the laws, every exponent, every coefficient, every mathematical structure appears calibrated for function. The laws are not arbitrary descriptions. They are precise prescriptions for a working universe. Now let me consider what this means for the concept of necessity versus contingency. Philosophers distinguish between necessary truths, things that couldn't be otherwise, and contingent truths, things that happen to be true but could have been different. Mathematical truths are typically considered necessary. 2 + 2 = 4 couldn't be otherwise. The square root of 2 is irrational necessarily. These truths follow from the nature of mathematics itself. Physical truths are typically considered contingent. The speed of light is 299,792,458 meters per second, but it could have been different. The electron mass is what it is, but nothing seems to require that specific value. But the fine-tuning challenges this view. If the constants couldn't have been significantly different without destroying the possibility of complexity, are they really contingent, or are they constrained, perhaps even necessary, by requirements for function? This is a deep question. The constants appear to have the values they do not by accident, but because those values are needed. Needed for what? For complexity? For structure? For the kind of universe that can contain observers like us? This suggests a form of necessity we haven't fully understood. Not logical necessity, the constants aren't mathematical truths, but functional necessity, the constants have the values required for function, for working, for producing outcomes, rather than chaos. If this is right, the distinction between necessary and contingent becomes blurred. The constants are contingent in the sense that we can imagine different values, but they are necessary in the sense that different values wouldn't work, wouldn't produce a functional universe. This is a new kind of necessity, teleological necessity. Necessity based on purpose or function. The universe has the structure it does because that structure is required for what the universe does. Now let me explore what this means for the concept of information. Information is a central concept in modern science. It appears in physics, biology, computer science, and many other fields. And it's intimately connected to the question of randomness versus design. Random systems have low information content. A random sequence of letters, X, K, Q, M, W, P, L, S, B, F, contains little meaningful information. It's just noise. Design systems have high information content. A meaningful sentence, "The universe is not random," contains significant information. The arrangement of letters specifies something, means something, functions to convey a message. The universe, we've established, is not random. It has the hallmarks of design, precise specification, functional organization, purposeful structure. This suggests that the universe has high information content. But where does this information come from? In ordinary experience, information comes from intelligent sources. A book contains information because an author wrote it. A computer program contains information because a programmer coded it. Information implies an informer, a source, that specifies the arrangement. Does the universe's information imply an informer? This is, in different language, the design argument. The information and the fundamental constants, the specification that makes the universe work, seems to require a source. The multiverse offers an alternative. The information comes from selection, not specification. Among all possible universes, we necessarily observe one with the right information for our existence. The information is selected, not designed. But this doesn't eliminate the information, it just explains how we came to observe it. The information is still there, still remarkable, still requiring explanation. Deeper theories might show that the information is derivable, that the constants follow from more fundamental structures that contain even more information. But this pushes the question back, where does that deeper information come from? The information problem is another way of stating the fine-tuning problem. The universe contains information-specified complexity, functional organization that cannot be explained by randomness. Something put that information there. Now, let me consider what this means for the nature of mathematics. Mathematics plays a strange role in physics. Physical laws are mathematical, they are expressed in equations, they involve numbers and relationships, they have mathematical structure. But why should this be? Why should the universe be mathematical at all? This question, which physicist Eugene Wigner called the unreasonable effectiveness of mathematics, is one of the deepest puzzles in science. Mathematics is abstract, it deals with pure forms, ideal relationships, logical structures. The physical world is concrete, it consists of matter, energy, space, time. Why should abstract mathematics describe concrete reality? The fine-tuning deepens this puzzle. Not only is the universe mathematical, but it's mathematically precise. The constants are specific numbers, not approximate, not variable, but exact values that determine everything. This precision suggests that mathematics is not just a description of the universe, but somehow fundamental to it. The universe doesn't just happen to be mathematical. It is intrinsically mathematical, essentially mathematical, mathematical at its core. Some physicists and philosophers have taken this idea seriously. Max Tegmark has proposed the mathematical universe hypothesis, the idea that the universe doesn't just obey mathematics, but is mathematics. Physical existence and mathematical existence are the same thing. In this view, the universe exists because it's a mathematical structure, a consistent set of relationships that, by virtue of its consistency, has reality. The constants are what they are because they're part of this structure determined by mathematical necessity. This is a radical idea, and it faces serious objections, but it attempts to explain the deep mathematical character of reality, including the fine-tuning by grounding physics in mathematics itself. Whether or not the mathematical universe hypothesis is correct, it points to something important. The universe's mathematical precision is not random. Mathematics is not arbitrary. It has internal logic, internal constraints, internal necessity. If the universe is essentially mathematical, its structure is not accidental, but follows from mathematical truth. Now let me explore what the impossibility of randomness means for the concept of existence itself. Why does anything exist? This is perhaps the deepest question philosophy can ask. Why is there something rather than nothing? The fine-tuning bears on this question in an important way. It tells us that existence is not cheap. A universe that contains complexity, that produces structures and functions, that permits observers like us, such a universe is rare, special, finely tuned. Most possible universes would be sterile. Most random arrangements of constants wouldn't produce stars or atoms or chemistry. The space of possible universes is vast, and the life-permitting region is tiny. This means that our universe is not just any existence, it's a very particular kind of existence. It's existence that works, existence that produces outcomes, existence that generates complexity and consciousness. This bears on the question of why there is something rather than nothing. If existence were random, any possible world would be equally likely, including worlds with no structure, no function, no observers. Such worlds would dominate the space of possibilities. But our universe is not such a world. It's a working world, a functional world, a world that produces extraordinary outcomes from simple laws and constants. This suggests that existence itself is not random. The particular existence we observe, this particular universe with these particular properties, is selected, specified, designed in the broad sense I've been using. Some might object that we observe this universe because we couldn't observe a sterile one. This is the anthropic response. We necessarily find ourselves in a life-permitting universe. But the anthropic response doesn't explain why there's a life-permitting universe to observe. It doesn't explain why the space of possible universes includes functional ones, or why the actual universe is one of them. It explains our observation, not the existence of what we observe. The impossibility of randomness thus points toward a deeper fact about existence. Existence is not arbitrary. Reality is not chaos. Something determines what exists and how it exists. Something that produces function, structure, complexity, consciousness. What that something is remains mysterious. Design, selection, mathematical necessity, these are candidates. But the mystery is not whether randomness is the answer. Randomness is not the answer. The universe cannot be random. Now let me consider what this means for the emergence of complexity. The universe began in a state of extreme simplicity, a hot, dense, uniform plasma of particles and radiation. From this simple beginning, complexity has emerged. Atoms, molecules, stars, planets, life, consciousness. This emergence of complexity is remarkable. The second law of thermodynamics tells us that entropy tends to increase, systems tend to become more disordered over time. How does complexity emerge in a universe trending toward disorder? The answer involves the interplay of energy flow and the laws of physics. When energy flows through a system, like sunlight flowing through Earth's biosphere, local pockets of order can form even as overall entropy increases. The emergence of complexity is compatible with thermodynamics, though it requires special conditions. But those special conditions themselves require fine-tuning. The laws and constants must be precisely calibrated to allow energy flow, to permit the formation of structures, to enable the processes that generate complexity. If the constants were different, complexity might be impossible. There might be no stars to power energy flow, no atoms to form structures, no chemistry to enable life. The emergence of complexity is not guaranteed by physics, it's permitted by fine-tuning. This means that complexity is not an accident. The universe is set up, calibrated, specified, designed to produce complexity. Complexity is not fighting against the laws of physics. It's enabled by them, facilitated by them, perhaps even intended by them. This is a profound shift in perspective. We often think of complexity as arising against the odds, as a rare and precious emergence in a hostile universe. But the fine-tuning suggests the opposite. The universe is friendly to complexity, calibrated for complexity, structured to produce complexity. The emergence of complexity is not an accident, it's the point. Now let me explore what this means for the emergence of life. Life is the most dramatic form of complexity we know. A living organism is an intricate arrangement of molecules, performing thousands of coordinated chemical reactions, maintaining itself against entropy, reproducing, evolving. The origin of life remains mysterious. We don't know exactly how non-living matter first became living matter, but we know it happened at least once on Earth about 4 billion years ago. The fine-tuning bears on this mystery. Life requires specific conditions: liquid water, organic chemistry, energy sources, stable environments. These conditions require the right physical constants, the right strength of forces, the right masses of particles, the right properties of atoms. If the constants were different, life might be impossible. Not just Earth-like life, but any life, any self-replicating, metabolizing, evolving system. The universe's hospitality to life is not guaranteed. It's a consequence of fine-tuning. This suggests that life is not an accident. The universe is set up to permit life, to enable life, perhaps to produce life inevitably. Life is not an improbable fluke in a hostile cosmos. It's a natural outcome in a cosmos calibrated for complexity. Some scientists resist this conclusion. They argue that life is a chemical accident, that it arose by chance from random molecular interactions, that it has no special significance. But the fine-tuning challenges this view. If the universe is set up to permit life, then life is not accidental, it's expected, it's natural, it's what the universe does. The chance origin of life occurs within a framework designed to make that origin possible. This doesn't mean life was inevitable on Earth, or that life exists everywhere in the universe. Chance still plays a role. But the role of chance is constrained by a structure that permits life, by constants that enable life, by laws that welcome life. Life is not an accident. It's an expression of the universe's deep structure, a structure that cannot be random. Now let me consider what this means for the emergence of consciousness. Consciousness is the deepest mystery of all. We are aware. We experience. We have an inner life, sensations, emotions, thoughts. This inner life is the most immediate fact of our existence, yet it's profoundly puzzling. How does consciousness arise from matter? How do physical processes in the brain give rise to subjective experience? This is the hard problem of consciousness, and despite decades of research, we have no satisfying answer. The fine-tuning adds another dimension to this puzzle. Consciousness requires a specific kind of matter, complex, organized, information processing matter. This matter requires specific physical laws and constants. Change the constants, and consciousness supporting matter might be impossible. This suggests that consciousness is not an accident. Like life, like complexity, consciousness is enabled by fine-tuning. The universe is calibrated to permit minds, to produce beings who can think, feel, wonder. Some physicists have taken this further. They suggest that consciousness might be fundamental, not an emergent property of matter, but a basic feature of reality present from the beginning. In this view, the universe's fine-tuning for consciousness is not coincidental. The universe is structured to produce consciousness because consciousness is somehow essential to the universe. Mind and matter are intertwined at the deepest level. This is a controversial idea, and it goes beyond established physics. But it's motivated by the same puzzle we've been exploring. The universe cannot be random, and it appears calibrated for conscious observers like us. Whether consciousness is fundamental or emergent, its existence points to the same conclusion. The universe is not arbitrary. It has the specific structure needed to produce minds and that structure cannot be explained by chance. Now let me explore what this means for the concept of purpose. Purpose is a concept we usually apply to actions and intentions. A hammer has a purpose to drive nails. A book has a purpose to convey information. These purposes derive from human intentions. They are not intrinsic to the objects themselves. But the fine-tuning suggests that purpose might be deeper than human intention. The universe appears structured to achieve outcomes, complexity, life, consciousness. These outcomes are not arbitrary. They are specific, predictable, recurring, wherever conditions permit. If the universe is structured to produce these outcomes, does the universe have a purpose? This is a profound question, and different worldviews give different answers. In the design worldview, the universe has a purpose because it was designed by a purposeful being. God, or whatever we call the designer, intended the universe to produce complexity, life, consciousness. The purpose is external, derived from the designer's will. In the multiverse worldview, purpose is an illusion. The universe appears purposeful because we necessarily observe a purposeful seeming universe. But there's no actual purpose, just selection among random possibilities. In the deeper theory worldview, purpose might be intrinsic. If the universe is essentially mathematical, and mathematics has a kind of necessity, then the purpose of the universe is to instantiate certain mathematical structures. This is not purpose in the intentional sense, but it's not randomness either. In each worldview, the fine-tuning is real. The universe genuinely appears designed. The question is how to interpret that appearance. I find it significant that all the major explanations for fine-tuning involve something other than chance. Design invokes intention. The multiverse invokes selection. Deeper theories invoke necessity. None of them attributes the fine-tuning to random accident. This suggests that purpose, or something like purpose, is inescapable. The universe acts as if it has a purpose, produces outcomes as if intended, structures itself as if designed. Whether this as if reflects actual purpose depends on which explanation is correct. But randomness is ruled out. The universe cannot be a random arrangement that happens by accident to work. The working is too precise, too functional, too effective. Something ensures that the universe works, call it design, selection, necessity, or something else. Purpose, or its functional equivalent, appears built into reality. Now let me consider what this means for human significance. For centuries, science seemed to diminish human significance. Copernicus showed that we're not at the center of the solar system. Darwin showed that we're not separate from other animals. Modern cosmology showed that we inhabit a tiny planet orbiting an ordinary star in an unremarkable galaxy among billions. This cosmic perspective can feel humbling, even crushing. We seem insignificant specks of matter in an indifferent universe, here by accident, destined for oblivion. But the fine-tuning reverses this picture. The universe is not indifferent to our existence. It's calibrated for our existence, structured precisely to permit beings like us the fundamental constants, the laws of physics, the mathematical architecture of reality, all are tuned to allow complexity, life, consciousness. This doesn't mean the universe was created for us specifically, but it does mean that beings like us are not accidents. We are natural products of a universe designed in some sense to produce us. This is a radical reframing of human significance. We are not insignificant specks. We are the universe's way of knowing itself. We are complexity becoming conscious, matter becoming mind, the cosmos waking up. The physicist Freeman Dyson put it this way: the universe in some sense must have known we were coming. This is not mysticism. It's a reflection on the fine-tuning. The universe's structure anticipates our existence not in time but in logic. The conditions for our existence are built into the fundamental laws. This doesn't answer all questions about meaning and purpose. We still have to decide what our lives mean, what purposes we pursue, what values we hold. But it provides a context, a cosmos, that permits and perhaps welcomes our existence rather than one that is hostile or indifferent. Human significance is not undermined by cosmic vastness. It's underwritten by cosmic structure. Now let me explore the relationship between fine-tuning and the laws of thought. Logic and mathematics are tools we use to understand the universe. But they're more than tools. They seem to reflect something deep about reality itself. Logical laws like the law of non-contradiction appear to be universally valid. A thing cannot both be and not be at the same time in the same respect. This is true not just for us, but for any possible reality. Mathematical truths appear similarly universal. The properties of numbers, the relationships of geometry, the structures of algebra, these seem to hold necessarily in any possible world. The fine-tuning suggests that physical reality is constrained by these logical and mathematical truths. The universe must be logically consistent. It must conform to mathematical structures. The space of possible universes is not limitless, but bounded by the laws of thought. This connection between mind and reality is striking. The same logical and mathematical structures that characterize our thinking also characterize the cosmos. The universe is intelligible. It can be understood by minds because it shares the same rational structure that minds possess. This is not coincidence. The fine-tuning suggests that rationality is fundamental, built into the universe at the deepest level. The universe is not absurd, not chaotic, not random. It is rational, ordered, lawful, and we, as rational beings, are able to comprehend this rational order. Our minds are not foreign to the universe. They are consonant with it, attuned to it, capable of grasping its structure. This has implications for knowledge. Scientific knowledge is possible because the universe is lawful and our minds can discern laws. This possibility is not guaranteed. It depends on the universe being the kind of thing that can be known and our minds being the kind of thing that can know. The fine-tuning ensures both. The universe is structured for knowability, and we are structured for knowing. This fit between mind and world is part of the larger design, the comprehensive calibration that makes the universe work. Now let me consider the implications for the relationship between science and other ways of knowing. Science has been spectacularly successful at discovering the structure of the universe, from atoms to galaxies, from quantum mechanics to general relativity. Science has revealed a cosmos of extraordinary precision and beauty. But science has limits. It describes what is and how it works, but it struggles with why. It can discover the fine-tuning, but not explain it. It can measure the constants, but not say why they have their values. This is where philosophy and perhaps theology become relevant. The question of why the universe is fine-tuned is not a purely scientific question. It involves considerations of meaning, purpose, design, necessity concepts that go beyond empirical investigation. This doesn't mean science is wrong or limited. It means that reality is richer than science alone can capture. The fine-tuning points toward this richness, toward questions that science reveals but cannot fully answer. Different traditions offer different answers to these questions. Religious traditions speak of divine creation and providence. Philosophical traditions speak of necessary being and sufficient reason. Scientific traditions speak of multiverses and selection effects. The fine-tuning doesn't arbitrate between these traditions. It doesn't prove God exists or doesn't exist, doesn't establish the multiverse or rule it out. But it does establish something important. The universe is not random, and explaining it requires going beyond chance. This common ground, the impossibility of randomness, might be a bridge between scientific and non-scientific perspectives. Whatever our worldview, we must grapple with a cosmos that appears designed, that functions as if intended, that cannot be explained by accident alone. Now let me explore what the impossibility of randomness means for the future. The universe has a history from the Big Bang through the formation of galaxies, stars, planets, life, consciousness. This history reveals a pattern: increasing complexity, increasing organization, increasing information. Will this pattern continue? The second law of thermodynamics predicts that entropy will increase, the universe will trend toward disorder. Eventually, stars will burn out, matter will decay, the cosmos will reach a state of maximum entropy called heat death. But the fine-tuning suggests something more interesting. The universe is calibrated to produce complexity not just in the past, but potentially in the future as well. The same laws that enabled stars and life might enable further developments we can't yet imagine. Life is characterized by its ability to create local order against the entropic tide. Consciousness is characterized by its ability to understand and manipulate the world. Technology extends this ability, allowing us to reshape matter and energy in increasingly sophisticated ways. If this trajectory continues, the future might see complexity beyond anything we've experienced. Mind might spread through the cosmos, organizing matter on scales we can barely conceive. The universe might not decline into heat death, but transform into something new, a cosmos shaped by intelligence rather than blind physics. This is speculative, but it's grounded in the fine-tuning. A universe calibrated for complexity might be calibrated for continued complexity, for escalating complexity, for complexity without limit. The impossibility of randomness thus has implications not just for the past, but for the future. The universe is not winding down arbitrarily. It's evolving along a trajectory established by its fundamental structure. That trajectory has produced us, and it might produce much more. Now, let me consider the deepest question. What does it all mean? The fine-tuning reveals a universe that is not random, a cosmos of precision, function, design. But what does this reveal about the nature of reality? One interpretation is that the universe is created, brought into existence by a being with intentions and purposes. The fine-tuning reflects design because there is a designer. This is the theistic interpretation, and it has been held by many of the greatest scientists in history. Another interpretation is that the universe is one among many, a member of a vast multiverse selected for observation by our existence. The fine-tuning reflects selection, not design. This is the naturalistic interpretation, increasingly popular among cosmologists. Another interpretation is that the universe is necessary, that mathematical and logical constraints determine its structure. The fine-tuning reflects necessity, the inevitability of certain structures. This is the rationalist interpretation with roots in ancient philosophy. Another interpretation is that the universe is mental, that consciousness is fundamental, and physical reality emerges from or depends on mind. The fine-tuning reflects the universe's inherent mentality. This is the idealist interpretation, also with ancient roots. Each interpretation has strengths and weaknesses. Each explains some aspects of the fine-tuning while struggling with others. No interpretation is definitively established by the evidence, but all interpretations share one thing: they reject randomness. Whether the universe is created, selected, necessary, or mental, it is not random. Its structure is not accidental, but meaningful, not chaotic, but ordered, not arbitrary, but specified. This common rejection of randomness is the core finding. Whatever else we believe about reality, we must believe that it is not random. The evidence compels this conclusion. Everything is designed not necessarily by a conscious designer, but in the sense that everything exhibits design's hallmarks. The universe is precise, functional, calibrated, effective. It works, and working arrangements cannot be random. Now let me bring this exploration to a close with some final reflections. We began with a simple observation. The fundamental constants of physics are fine-tuned. Change them slightly, and the universe becomes sterile. No atoms, no stars, no chemistry, no life. From this observation, we derived a profound conclusion. The universe cannot be random. The fine-tuning is too precise, too functional, too specific to be accidental. Something other than chance is responsible. We explored the possible explanations: design by an intelligent being, selection in a multiverse, derivation from deeper principles, or logical and mathematical necessity. Each explanation has merit. None is definitively established, but the impossibility of randomness is established. Whatever the correct explanation, it's not random chance. The universe is structured, specified, designed, in the broad sense organized to produce complexity, life, consciousness. This conclusion has profound implications. For physics, it suggests that the fundamental constants are not arbitrary parameters, but clues to deeper truths. Understanding why the constants have their values might lead to revolutionary new physics. For philosophy, it raises questions about necessity, contingency, purpose, and meaning. The traditional frameworks may need revision to accommodate a universe that cannot be random. For theology, it provides evidence, though not proof, for purposeful creation. The fine-tuning is consistent with design, even if it doesn't conclusively establish a designer. For human self-understanding, it reframes our significance. We are not accidents in an indifferent cosmos, but natural products of a universe structured for our emergence. The universe is not random. This is the conclusion that the evidence compels. The implications are vast, the questions are profound, and the exploration has only begun. Everything is designed, the constants are calibrated, the laws are specified, the universe is ordered. This is not the end of inquiry, but the beginning. Knowing that the universe cannot be random, we can ask, what is it? How does it work? Why is it this way? These questions will occupy humanity for generations, perhaps forever. But we pursue them in a cosmos that permits understanding, that welcomes inquiry, that rewards the search for truth. The universe is not random. And that fact, that remarkable, undeniable, consequential fact, changes everything. We are not accidents. We are not flukes. We are not meaningless specks in an indifferent void. We are the universe, understanding itself, the cosmos becoming conscious, matter becoming mind, randomness becoming order. The fine-tuning made us possible. And now we can see that it was never random, never could have been random, but specified, calibrated, designed. Everything is designed, and we are part of the design.